Hello everyone. This lesson will actually be the last lesson for the energy section of the course. We're going to talk today about, or in this video, about thermal energy and heat. So what is thermal energy? Thermal energy is related to the total kinetic and potential energy of the atoms or molecules of a substance. So if you have a cup of water that has, let's say, been heated to a certain temperature, the molecules of water in that cup are going to have started moving faster and faster inside. That's going to give the molecules kinetic energy. Now there's also potential energy in the atoms, because as the atoms are moving around, they're going to get closer and closer to each other, but the electric repulsion between the protons and the protons of the different atoms are going to push each other away, so there's potential energy stored in there as well. So the total of all of that energy is what's called thermal energy. What is heat? Now, thermal energy and heat are often mistaken for each other. Heat is actually the transfer of an energy from a warmer substance to a colder one. It's almost like it's a verb. But we often say, and I will actually say it as well, using it as a noun, where it's the heat in the room. Well, technically that's not the right wording. Often what we mean also by the word heat is the word temperature, which is often mistaken for these as well. So what is temperature? Well, temperature is actually the measure of the average kinetic energy only of the atoms or molecules of a substance. So all three of these are very closely related, but they are different. We're most used to temperature, but we actually often use the word heat as a substitute for the word temperature. And it's kind of like the whole idea of weight and mass. It's similar to that. But temperature, when you're reading off of a thermometer, what you're reading is the average kinetic energy of the atoms or molecules of the substance or the room. Whereas if you use the word heat, you're supposed to be talking about the transfer of energy from a warmer substance to a colder one. There are three methods of heat transfer: conduction, convection, and radiation. Conduction is done through the collision of atoms with one another, and oftentimes we will use metal as an example of the word conduction, because if you ever put a metal spoon in a hot bowl of soup, especially if you're cooking the soup, if you just leave the metal spoon there and come back and grab it, you can burn yourself, because the metal will be at some point just as hot as the boiling soup will be. So the reason for that is if you have a metal bar of any kind, or any kind of good conductor of heat, metal is one of the best ones. If you put a fire at one end of that metal, what'll happen is the molecules inside of the metal at that end will start to move faster and faster. And as they move faster and faster, they'll hit the molecules next to them, which will hit the molecules next to them, which will hit the molecules next to them. So the energy, the kinetic energy of those molecules is going to increase the kinetic energy of the molecules next to them as they continuously get heated by the fire. And at some point, that energy will reach the other end, and that is called conduction. So we call conductors in electricity materials that allow electrons to flow through, but it's not the same thing. Here it's actually just the atomic molecules that are vibrating and hitting the molecules next to them, which transfers the energy all the way across. So it's not quite the same thing, similar, but this is done with, and you can call this heating, because you are transferring energy from one end to another of the bar. Okay. Convection is a circulation of fluid particles. Now, fluid can be water, but it can also be a gas like air. If you open the door of a warm house on a cold day, what's going to happen is the warm air inside the house is moving faster molecularly at a molecular level. It's going to start hitting the colder molecules of air on the outside of the house, start to transfer the energy to them, and if you actually shut off all the heating in the house, what would happen eventually is all of the molecules that are moving fast in the house are going to lose their energy to the colder molecules outside, and eventually all of that warm air is going to cool down because of that loss of energy. And what usually happens is warm air will rise and cold air will fall. So you'll end up with a circulation of the warm air upwards and the cold air downwards. And if you leave the door open too long, eventually the whole house will become cold because of that. You'll also see this outside. If you have pavement in the summertime getting heated up by the sun, and we'll get to how that works in a second, but that'll heat up the air above the pavement, and that hot air will rise up, and you'll actually see the waves of that rising air being replaced by cooler air from above as these little like kind of illusion. They almost look like illusions of air waving right above the pavement, which can also cause the illusion of looking like there's water on top of the pavement. So that's basically the cause of all of that. With radiation, the transfer of energy is done by electromagnetic waves. But this is not sound because you don't actually need particles for this to happen. When we talk about radiation, it's strictly electromagnetic waves for thermal energy to be transferred. So something like a microwave. For the sun, for instance, to heat up the earth, the warmth of the sun reaches the earth without traveling through a medium, right? Space doesn't have any particles in it. So that's proof that the energy can be transferred without actually having to affect particles in between. There's no particle contact. So it's completely different than conduction, where you absolutely need particle contact, whereas for radiation, you don't. Campfire outside actually gives off energy in all three waves. Campfire can conduct heat if it's in contact with metal. A campfire can produce convection of warm air rising and cold air replacing it, so you can feel that convection sometimes of heat. And the radiation, even if you were out in space, a fire would still heat you because of the infrared radiation coming off of it. So a fire is actually kind of an example where you can have all three different types. The equation for heat transfer is Q is equal to mc delta T. This is an equation that's also used in chemistry classes. Q stands for the quantity of heat gained or lost. M is the mass. Now we got to be careful with C here. We've talked about C as being the speed of light in other units. Here, you have to understand within the context of this equation, it's a completely different variable. It's called the specific heat capacity of the material, and we'll talk about that a little bit more in a second. And then delta T, you'll notice I use the capital T here. Some textbooks do use a lowercase t, but that makes it look a lot like time. So I'm using capital T to represent the change in temperature. The delta is needed because often the temperature is not going from 0 to the higher temperature. But if you did have 0 as one of the temperatures, you could drop the delta here. So what is the specific heat capacity? Well, every substance has a different specific heat capacity. So for glass, if you look at the units here for the specific heat capacity, it's in joules per kilograms degrees Celsius. And the reason you have that constant in the equation is to get rid of the kilograms for the mass, get rid of the degrees Celsius for the temperature, and give you joules to allow Q to be a joules value. So Q is a quantity of energy measured in joules. So we require that to happen with this unit, okay? So glass has a different specific heat capacity than iron, and then brass, then lead. Water is one we use quite often, the 4.18 times 10 to the 3, because we talk about, and especially in high school, we often will work with water. So these are common heat capacities. You can see the page number in your textbook to find that table. So I could ask a question now: how much heat is required to raise the temperature of 2.2 kilograms of water from 20 degrees Celsius to its boiling point? So if we write down the information that's given to us in the question, the mass is 2.2 kilograms. We have a change in temperature, right? So delta T is equal to the change in temperature, T2 minus T1, which would be, what is the boiling point of water? Well, that is 100 degrees Celsius, and we're starting at a temperature of 20, so my delta T is 80 degrees Celsius here. What is the C of water? On the previous page, we saw that that's 4.18 times 10 to the power of 3, and I'm going to write the units down here: joules per kilogram degrees Celsius. And oftentimes you'll see specific heat written with a subscript to remind you as to which specific heat you're talking about. It also differentiates it a little bit more from the speed of light unit, variable that we've seen in other units. So oftentimes a little subscript will be put beside the specific heat capacity. And it's asking how much heat is required to do that. So what is the transfer of energy? Well, that is your Q value. And it's just a direct substitution into the equation mc delta T here. So if I put all of those numbers in there, you'll notice that it is in kilograms, and it has to be in kilograms. So if it ever isn't, you have to convert. Make sure your units are all in the proper units. So this is 4.18 times 10 to the 3 and 80. And if you look at how the units work, we've got, I'll just do unit analysis next door here, kilograms, and then joules per kilogram degrees Celsius, and then times degrees Celsius. So the degrees Celsius cancel out, the kilograms cancel out, and you're left with joules as your final unit. So if I do this calculation off to the side here, 2.2 times 4.18 to the power of 3 times 10 to the power 3 times 80, and that gives 735,680 joules, which, if we wanted to, we could write as approximately 736 kilojoules of energy. So once the joule values start to get really big like that, you will sometimes see the answer being converted to kilojoules. You don't have to do that, but it often is done. You could also write it as 7.36 times 10 to the power of 3 joules. That would be another way that you could do this, rounding it off to 3 or 2 decimal places depending on what the number of significant digits are. So not a very difficult equation to use. Again, you could be asked to find the change in temperature if you were given the mass and the energy. So there's different ways that you can rearrange this equation. I'm going to leave you experience that with some of the homework questions. Here's a good question that kind of mixes both what we learnt in electricity along with what we're learning now with energy. Since transfers of energy can happen between different types of energy, here we have a situation where you're having electrical energy transformed into heat energy to heat a cup of water. So it says an electric immersion heater is placed in 500 grams of water in a cup. The water is heated from 10 to 90 degrees Celsius. If the heater is 65% efficient, how much energy does it put into the water to heat it? So for part A, this is kind of a two-part question, because the first thing we need to do is find out how much energy is required to heat the water. And then the second thing we're going to do is find out how much energy in electrical energy is required to do that if you only have a certain efficiency. So let's do the Q is equal to mc delta T to find out what the amount of energy is required first. So in this case, we have 500 grams of water Instead of listing the numbers here that I usually do, I'm just going to do it right in the formula. Now, we have to convert grams to kilograms, so that's 0.5 kilograms. The C of water is again the 4.18 times 10 to the power of 3, I believe it was. Yes. And there's our joules per kilogram degrees Celsius. And then our change in temperature is 90 minus 10. I'll write it out fully here so you can see that. Once again, degrees Celsius are going to cancel out, kilograms are going to cancel out, and we're left with just joules here. Now 90 minus 10 is just 80. So I'll do all of that on my calculator here. So 0.5 times 4.18 times 10 to the power of 3 times 80. And that's giving me 167,200 joules, which again we could write in another format if we needed significant digits. I'm going to keep that number as is though, because we do need it for the second part of the question as well. So that's how much energy is required to raise the temperature of water. Now for the efficiency part, sorry, this is still part A. Let's call this I and 2I. If it's only 65% efficient, remember that usually we need to put more energy into something in order to get the required energy that we need. So we're going to actually use more than 167,200 joules. The efficiency equation is usually equal to the amount of energy outputted by the system divided by the energy inputted to the system times 100%. Now, the outputted energy is the useful energy, and the inputted energy is the larger amount put in. So you're always going to have a bigger number on the bottom than at the top, okay? So this 167,200 is our useful energy. That's how much energy we're getting out of this scenario. But we're going to have to put more energy than that in there. So in this case, we know the efficiency is 65%. We're trying to find how much energy is going in. So can we rearrange this equation to get our E in all by itself? Well, all we have to do, because everything is multiplying on this side, is take the En and move it over to this side. So the E in is going to be equal to the E out divided by the efficiency times 100%. So what that'll look like is this. We're going to have 167,200 divided by 65% times 100%. Now, let's just talk about the percentages here for a second. If I wrote just the times 100% over here, just for a second, and the divided by 65%, just to talk about how this works, okay? Remember that 100% as a decimal is just 1, and 65% as a decimal is just 0.65, okay? So really what we're doing here is we're just dividing by 0.65. Would we get the same answer if we just canceled out the percentage symbols here? And the answer is yes, because 100 divided by 65 is the same thing as taking, if I divided both the top and the bottom by 100, which doesn't change the fraction, it's the exact same thing as just divided by 0.65. Okay, so a little bit of math here just to explain how things are working out. Some students are going to want to change 65% into 0.65 because that's usually what we do. 100% also has to change to 1 if you do that, however. Okay, or I just proved to you that what we can do is just cancel out the percentage symbols. So this is almost like canceling out units, okay? The percentage here and the percentage here cancels out. So I'm going to do that calculation off to the side here of 167,200 divided by 65 times 100. And I should get the exact same answer as if I took the top number and divided it by 0.65. So 167,200 divided by 65 times 100. And my answer should be bigger than the outputted energy, which it is 257,230.7692. Okay, which we could round off to our significant digits. Again, I'll let you do that, but for the next part of the question, I'm actually going to use the full number to calculate the answer, because again, I don't want to carry rounding errors all the way through. All right. So what is the next part of the question? Calculate the current that the heater must draw if the emergent heater is run off of a 12-volt battery. So we're looking for an I value given that the voltage is 12 volts. Now, how are we going to do that? Well, because the answer to this question is in joules, even though this is joules of heat, we can relate any energy type to any other energy type because of the law of conservation of energy. This energy came from an electrical circuit. Okay, that's what produced that amount of heat. So this basically is the electrical energy. So do we have an equation for electrical energy? Well, the answer to that is yes. Now, we also want that equation to have V and I in it, because the V and the I are given to us in the equation, and we're looking for I. So we need an equation that relates all of those things for us. Now I just realized that there is a quantity missing here. We also need the amount of time for which this thing is submerged, because the equation that we are going to use is going to be the following one. VI times the time. Okay, so I'm sorry, I forgot to put that quantity right at the top. So let's say that this immersion heater is placed in the cup of water for 5 minutes. Okay? We need that time value. It's the only way that we're going to be able to use this equation. So our time is 5 minutes. Let's rearrange the equation to get I. I is equal to E divided by VT. And remember, this is a lowercase t, so it is the time. Our energy value is going to be the energy that we calculated right here. So 257,230.7692. All divided by our voltage times our time. Now the voltage is in 12 volts, which is perfect, but our time is in minutes. So we need to calculate what is that time in seconds, because we are working in the MKS realm here. So we're going to do 5 times 60, which is 300 seconds. And our final answer is going to be in amps. So I'm going to do that calculation off to the side here. 257,230.7692 divided by bracket 12 times 300. And the amount of current required to do this is going to be 71.5 amps approximately. So with all of our knowledge of the different types of energy and the law of conservation of energy, we can now solve a much more complicated question such as this one by following, what we know about how to heat water with the Q value here. That gives us the amount of energy is required. The efficiency of the electric circuit is not great, so we calculated how much energy that would require, and it makes sense that it's going to be more. So we're pumping in a lot more energy to produce that heat. There are losses of energy here. And then we know the amount of energy in an electric circuit is given by VIT. Knowing all of those values, we are able to find out how much current is being used. So that is going to end the unit on energy. There will be some work attached to this, so please be conscious of that.